Okay.
So there are some advantages to being older. Very few, but a few that you have had the opportunity to actually engage in a wide range of activities over your career, and that's kind of where I am. So this afternoon, in looking at the schedule, the other presentations, I decided that, this is about energy, water, and food production, and so it might make sense to back off and speak in a little bit broader terms. My own background is actually in the remote sensing end of things, and that's what my real job is. The other stuff is just service, like all the rest of academics do. And I noticed that, this conference, of course, is focused on the predominance of people come from imaging science, from computer science, from electrical engineering, and we have algorithms that we develop and we put on top of problems. We also have plant scientists here in this, an agronomist in this particular session, as well as people who are going to talk about other, and have talked about other kinds of problems other than phenotyping. So, but the one thing you haven't talked about really in a serious way is really data. And so I'm going to talk about this from 3 points of view. One, the data. It's not all RGB data or video data, my friends. The data and the sources, the platforms, the challenges. Then I'll move into the sensors component of it. And then I'll bring in at the end some opportunities as well as just some illustrative examples of where some of the algorithmic work has actually been making some progress. So I'd really like to start out by saying, we in remote sensing, we in algorithm development, we in plant sciences are just all one piece of this big picture. And it requires, in situ observations, which are by and large point measurements, and they're either limited and dense or they're sparse and extended. We have all kinds of remote sensing data inputs, which I'll talk about. We also have to think about this in the modeling context because predictive models of various sorts are by and large multi-scale. They require inputs of both remote sensing and in situ data, and as well as some exogenous inputs that might be provided from other sources. So the ultimate goal is this integrated sensing systems, which includes the computational component in agriculture. So let's back off and think about this first of all traditionally. So the sensor craft, and I put that in quotes, are by and large platforms that are from in space and aircraft that are all sizes. And our goal is to, in this context, to address a number of critical problems in agriculture. But there are other platforms that we might not be considering as remote sensing. So GPS, of course, is really important relative to positioning, but it's also becoming very important as an input because the signals of opportunity that are now being used from GNSS are providing information on soil moisture, etc. You may not have thought about this as being a remote sensing kind of a platform. It has the loving name Tom and Jerry, and it's associated with the GRACE mission. It's two sets of platforms that are basically accelerometers, and they are measuring the large-scale movement of water in the aquifers. We also, I'm sure everyone in the room has heard about the shuttle topography, radar topography mission, which got the first and only continuous digital elevation model of the world, accepting the areas that the shuttle doesn't travel on. So these are other platforms. Now, moving to the future, we have now the small sats, and the small sats are interesting not only from the point of view of the fact they don't cost as much, but from a point of view of what they can provide. So on the left, what you see is a traditional kind of a platform. So it's QuickScat that was had provided a lot of data over about a 10-year period, and it had a fixed orbit and got data at about 25 kilometers. What you see on the right is a mission that is Cygnus, which will launch this fall. It's an 8-satellite constellation, all small sats, and it's a GNSS reflectometry mission. Again, 25-kilometer resolution. But what you're going to see is rather than having one-day global coverage, you're going to have on the average, about on the median, is 1.5 repeat cycle in terms of the data. if you looked at that, you see that there's all kinds of issues that will come about, not only engineering issues to control those satellites, but data issues. How are we going to integrate that data in a reasonable way? How are we going to analyze it? And of course, now we have UAS. And so that came about in the context of agriculture because we've already seen and heard that and experienced that in-field monitoring is really expensive. And once you get to certain parts of the season, then access is really limited in many cases. So spaceborne sensors can contribute something, but they have fixed orbits, and many of them have passive sensors, and so they're impacted by cloud cover. Aircraft are better from the point of view of being able to fly when you need them, if you have enough money. But UAS is we saw a consumer grade platform, and they can potentially provide low cost information on demand. And everybody's playing in the game. Now, if we think about this as sensor craft for agriculture, kind of where we are and where we're going, then most of these sensors on most of these platforms are simple platforms. They fly RGB cameras or maybe 4-band cameras, maybe up to a 6-band camera. They're always frame cameras, and they're covering the visible near IR, and a few of them cover the thermal. The data products are geometrically corrected using commercial software, and it's pretty good. Depends on what your problem is as to whether it's adequate. I get a lot of farmers saying, it just doesn't overlay. Well, there are a lot of issues with UAVs, particularly in the Midwest where you have a lot of wind. You might get some GIS kind of products that would be coming from true color overlays. Maybe you'll have some band ratios. The most typical is NDVI, but NDVI is not a high fidelity product. Depends on what your filter is on your camera. Most of these are popping blue filters on to cover the blue band to get a near IR. One NDVI is not equivalent to another, and it's not calibrated radiometrically. Sometimes you get photogrammetrically derived digital elevation models, but from that you can often get useful information, both visually and sometimes you can even use empirical modeling to predict some things of interest. Now, in terms of this as a sensor craft, there's a lot of interest, and the areas that are being focused on as a platform is to design application-specific platforms. Most people are, buying it from a catalog now, but that's not going to be the long term. We have autonomous guidance that's improving all the time, so you don't have to be an expert or a pilot to fly these. And perhaps the most significant contribution is one of two, and that's in the miniaturization of sensors. Advanced sensors are being miniaturized every day, and we're now even looking at nanotechnology in terms of the contributions to these sensors. When they're light and you can produce them in mass scale, they'll be cheap. Software is the second area that's certainly critical, and it's an area that a lot of people, including our group, spending a lot of time, and it's where I would say the predominance of the people that attend this conference would be interested, as well as development of the associated algorithms. Can't leave out proximal sensing. I already mentioned the fact that there is quite a bit of, that we need to consider in terms of in situ sensing, but proximal sensing continues to have its contribution as well. So that's the first part, thinking about the platforms. Now let's talk a little bit about some of the sensor technologies. So I already alluded to this in the context of UAS, but let's start with the space-based technologies first. So all of these, in one way or another, are sensing in some part of the spectrum. Most of what people are seeing right now is the visible near IR, but the microwave has a lot to contribute, and as well as the thermal. And so you'll see more and more sensing going on in those arenas in a more sophisticated way. The key trade-offs we have in all of these platforms and sensing technologies are really threefold. What you have in terms of spatial resolution, what you have in terms of temporal resolution, and what you have in terms of if you break up the spectrum in terms of the spectral resolution. And this is just an image from MODIS. You can see there's a change here about a third of the way through. It takes about 2 passes to cover the US. And MODIS is a polar orbiter. It sees every point on the Earth approximately twice a day. So there's a lot of data you can get, but it's coarse resolution. It has 2 bands that are 250 meters. Most of them are 500, and others are a kilometer, because it's studying the atmosphere, it's studying the oceans, and it's studying the land. And all of these applications have different requirements. It's also the most high fidelity. We've had a number of presentations already today that use MODIS. The products that are derived from MODIS data are really high quality. A lot has gone into them. Some of them are just data specific. Some of them include modeling. But the backbone in terms of medium resolution, because for most of us that are working in agriculture, 250 meters is too coarse unless you're looking at regional kinds of problems. So the long-term sensing has been from the Landsat satellites, and it started even before my career. Back in 1972, we had Landsat 1, followed by Landsat 2. NASA had a decent program. Every few years, you got a new one. Landsat 4, Landsat 5. Oops, what happened? Well, Landsat 6 failed on launch. Landsat 7 finally got up, and now we have Landsat 8. Everybody is thrilled that this is a long-term time series. Well, it is, but the sensors have changed over time. The sensors degrade over time, but still it's the best that we've got, and it's the best that anybody has at that resolution in the world. High spatial resolution, depending on what your application is, may be critical. And in the US, it's mostly commercial. Okay, if it's in space, for what we call high resolution, it's either going to be the military or it's going to be commercial. And the typical characteristics, interestingly, are similar to what we have at the very low end of the spectrum. So low end of the platform spectrum, where we're talking about UAS. So you have these very large data volumes because you have high spatial resolution, so you trade off the spectral information. They're usually 3 to 4 bands. They cover a small area, 10 to 20 kilometers, and they have some capability for actually extracting the textual information because they have a panchromatic band as well as the multispectral data. It's advancing, though, because if you look down here at the US commercial platforms, you see that WorldView 3 now has more than those 3 or 4 bands, and it's beginning to get useful. So it has it in the Wiener, the SWIR, and it has some other kinds of products that are used for correction. And WorldView 4 is going to launch soon. RapidEye's not a US platform, but it's actually a constellation. It's what you see on the right. It was launched for agriculture. All of these cost money, and sometimes they're worth it for some applications, and sometimes they're not for others. Okay, now looking to the future, these are some new sensors and platforms, missions. Water is going to be at the forefront. We all waited for a long time for SMAP. Okay, SMAP stands for soil moisture, active, passive. So radar is the best way to do soil moisture. All right, one of the problems is you go out in the spectrum, longer wavelengths, you have lower energy. And so you have to have bigger antennas and coarser spatial resolution. So passive microwave, which is one of the best ways to do it, actually turns out to be very coarse spatial resolution. The thing that SMAP did was they put a radar on it as well, and they were going to have radar-based inputs, and they were going to integrate that with radiometer, which is the coarse coarse passive microwave, and that was going to be great, and it was for about 3 months, and then the radar went out. So now they're still back to about 40-kilometer data, and the traditional sensor is operating magnificently, but it's not quite what we'd hoped for. So we're looking to the future, and actually what we're going to do is to try to use data from other radar platforms that the Europeans have up, not quite perfect because it's not a perfect match, but you keep going in terms of trying to improve what you've got. All right, so these are just some global products. All right, another one, and if you look at this carefully, you'll see that this is Louisiana yesterday. Okay, remember the big thunderstorm? Okay, the Global Precipitation Mission is something that has been a major advance in the US. NASA is finally going to get a radar up, but they're going to do it in combination with India, so Israel and NASA are working together. And it will have some water-based focus as well as be able to do a lot with biomass. And finally, further down the road in the waterfront, we have SWAT. They talk about sensing water. So in terms of water, if you think of water levels, then it's a radar altimeter of the oceans. But you don't ever hear about that relative to a lake or a river. Well, this is the kind of thing SWAT will actually work on, and it'll be an interferometer. So that's one kind of technology. So it's going to be the microwave. Let's move to a second technology that's getting a lot of interest in agriculture, and that's LIDAR. So people may be familiar with LIDAR in a greenhouse where you sit it down, you operate it, but it also operates from aircraft and from spacecraft. And these are ranging measurements. So what you do is you send out a pulse and then you measure the response. And it's very key. It's a very simple measurement. It's just time. Okay? You know where you are, you knew how long it took to send it out and come back, so you know where that object is. So just showing some examples from LIDAR technology, and hydrology is one of the areas that is of where LIDAR is of particular interest. At a very large scale, this is kind of a watershed scale, you see this is a photogrammetrically derived digital elevation model, followed by the SRTM model, a little bit better data. The third is LIDAR, where we've not extracted the vegetation yet. And then you look at the final product and you see that it's much higher detail. So there's lots of possibilities for this where you need high spatial resolution. And one of them might be in terms of smaller rivers where you have ditches for erosion, where you're for drainage. And lots of states are being flown with LIDAR. That's great. There's also still opportunities for the computer scientists and the computer engineers because the statewide products are not tuned to a specific application. And so you may get a product and you may test it and you may say, hey, this isn't any good for my application. It's not good enough in terms of resolution. But if you have people that understand the sensing and understand the computation and the algorithms, they can actually make great improvements. And this is an example which actually came from Indiana, where the statewide product was compared to an in-house product that was developed. The other thing that, some people, to one person's noise is another person's signal. So if you're a hydrologist, you want to get rid of the vegetation because the water goes under it, okay? But if you're a vegetation scientist, then what you want to do, whether you're a forester or you're a person who studies plant breeding, is you really want to know more about the plant structure. The height is the easiest one, but there are other kinds of information that can be derived from associated with the plant structure, because depending on the structure and the grouping of the plant, then what you'll find is different levels. You'll find gaps between clouds of data, et cetera, and that can be used for important kinds of predictions. It's been used effectively in forestry for leaf area index. This can also now be flown on LIDAR. This is from a LIDAR system in Indiana that flew last week, and it's at this point just for plant height. So second technology in terms of sensing was LIDAR. The third is trying to get at the chemistry. So if you start out and you have just a simple RGB camera, what you're going to get, let's look at a single band. That single band, all you have is an intensity, okay, for any pixel. But if you move to multispectral data in this little cartoon you have in the middle, then what you see is for every crop or every signature of a particular target, could be various kinds of crops, could be trees, etc., then you'll have in each spectral band a particular value. That's an approximation because these bands are, what you get is the integrated response over this range of wavelengths. When you move to hyperspectral data, what you get is the full detail in terms of the spectral response. Now, I'll talk a little bit about the Achilles heel also of hyperspectral data, which is where I spend a lot of my life. Okay, so just to show you Landsat, if we look at the windows, and these are the bands on Landsat, and you would have one value, and these are the responses over which you would be integrating. You catch a lot of that detail, but you miss a lot of windows as well. And that's true for all multispectral sensors. So when we talk about hyperspectral sensing platforms, then they're far and few between in terms of those that have delivered data to the civilian community. Hyperion was part of an experimental mission supposed to last a year, and it was launched in 2000, and they're slowly bringing it down because it's out of fuel. But everybody's begging for it because it's the only one from which you can actually get data if you're just a civilian scientist. But there are others that have provided limited amounts of data to the projects that launched them. There is a good news piece of this, though. If you look at the next list, you'll see that there's a lot of missions that are in the planning mode. It's not a simple thing, but by 2018, then there will probably be two, one from Germany and one from Japan, that will be launched providing regular data. The US has been trying for a long time. The sensor's ready to go, but it's a political issue. Ours is called HESPIRI. In terms of priorities of NASA and of Congress. We've never been able to sell the importance of hyperspectral sensing. Now, airborne spectrometers are widely available. You can fly them on aircraft, and we can even fly them on UAVs these days. There is actually a major research initiative at a major U.S. institution collaborating internationally with others on actually developing nanotechnology-based spectrometers. That's an example of what I mentioned before. This is just to show you what HESPIRI, for those of you that are young, will provide one day, as well as the kind of products that you'll get from other international spectrometers. So on the left, what you get is pretty much the sort of thing that we would get now from Hyperion, although it'll be better signal to noise. There's also going to be intelligent payloads on these platforms because if you want to have quick turnaround with low latency, then what you're going to have to do is do some processing on board to get the products of interest. The other thing that'll be really good is there'll be a thermal sensor, multispectral, not just one band. So there'll be a lot of interesting information for agriculture from HESPIRI. Now, the kind of opportunities that we have with this kind of data are numerous. So with this detailed signature, then what you can do is you can actually do a much better atmospheric correction. You can use radiative transfer models, and so you'll have a lot better reflectance estimates coming out. In terms of products, it's not surprising that you can do better classification, you can do better differentiation. Now, some people may not have thought of this, but you're not able to do unmixing by and large. Many of the pixels spatially have multiple kinds of objects within them, either mixed continuously or in terms of subsets of the pixel having different types of objects. So to unmix that, you can't really do it with multispectral data, but that's one of the opportunities for hyperspectral data. The first one, though, in agriculture that's going to be used and is currently of interest is narrowband indices. So if we look at this list that actually came from White back in a publication in 2012, then you see associated with phenotyping a number of traits, the various indices, and you see over on the right the narrowband wavelengths. So there's going to be a lot of opportunities for actually developing indices with atmospherically corrected data. So I'm going to show you just an example, and this is one that's important in the Midwest for mapping crop residue after the harvest. And that's important for a number of reasons, not the least of which is erosion to hold the soil from wind and water during the winter season until you plant again. And so this is near Purdue. And what you see is this area, we see residue of various sorts. And if you'll note, you'll see also various levels of soil versus residue within a particular spatial resolution element. This is an illustration of an index. So you see, if you come out there in the 2100, 2200 range of the spectrum, you see that dip, that absorption dip. And that absorption then can be used with the shoulders to actually come up with an index that will, the deeper it is, then the greater the amount of residue. And that's used very effectively. Another thing, as I already indicated, is that classification can be advanced dramatically with hyperspectral data. And so if we look at the left, you see this Landsat-based classification, which can really only do large groupings of forest in this particular case, whereas if you move to hyperspectral data, and there, of course it's not always guaranteed, but you can have a dramatically greater number of classes that you can successfully identify. So if we look at this in the context of agriculture and these various technologies, what you have with LiDAR is twofold. One, the heights of both the land, the digital elevation model, and the vegetation, and then some other kinds of important structures. Prior to that, though, if you look along the bottom, I have sensors, pre-processing, it's very critical that you get the geopositioning correct. And the higher the resolution, the more difficult that is. And then there are various products that can come out of that. Multispectral cameras also have pre-processing, although not necessarily as difficult as LiDAR or, as you'll see, hyperspectral. Provide stereo products, which you've heard a number of presentations on today. And also contributions to some of the same things that are geometrically oriented. You can get some basic multispectral indices, and from that, then the products you can contribute to are associated with plant biochemistry and plant physiology. And of course, the hyperspectral information can provide much of the same sort of thing, except you now have narrowband indices. So some of the challenges, okay, for the data science, and we're moving to the last part of the presentation where we're going to talk about analyzing the data. So some of the open issues have to do with high fidelity geopositioning, and that's critical because we're going to be dealing now with multiple sensors and a multi-temporal time frame. We also are trying to do this more cheaply, and so that creates trade-offs and challenges. The data integration, once you have it positioned correctly, that problem is not solved because there are other kinds of issues associated with the scale of the data, the information within the data. How do you fuse the data? Do you fuse the data or the data products, etc.? One of the most complex is going to be associated, and is currently associated with this water-related activities, because you have such coarse spatial resolution and you have very few, very sparse point sensors that are actually used. And so you may end up with a sensor within a very coarse spatial grid of 20 kilometers. What does that mean? So lots of downscaling that is going to require multiple sensor integration. There's also complexities of the data, but this is where many of the tools that we have developed, can actually contribute. And I'll show you just a couple of case studies associated with that. One of which is non-linearity, second of which is non-stationarity, third of which is high dimensionality. The more data we have in terms of spectral bands, multiple sensors, etc., the higher the dimension. And so, but it's not really, we call it the curse of dimensionality. Usually we do not have a space that's actually fully occupied by the data. It's a much lower intrinsic dimensionality. When we start labeling data, when we start classifying data, the best methods, if you can have it, will involve labeled data, will involve some ground truth, as we say, even though no ground truth is really truly true. But how do we exploit what we know already in an effective way? So case study one, and I'm going back to hyperspectral data as my example. So yeah, we had this continuous spectral response over some range of wavelengths, but we also have highly correlated adjacent bands. So what is an advantage is also a problem sometime. And what you look at over here in the lower right-hand corner is the correlation matrix for those bands. You see that in those spectral signatures, the highs being the reds, the lows being the blue, you have a lot of contiguous, highly correlated bands. The other thing you have are some very similar kinds of signatures that might be, so this particular one is the same class, but it's at two different time periods. Okay, and so it could be due to something that happened physiologically, or it could be due to the fact that even if it's supposed to be a stationary signature, that you have different atmospheric conditions, or if you had a spatial extent, you got your ground reference information in one area, but you're supposed to classify the whole scene. So all kinds of issues here that now you're suddenly going to have to deal with. One of the things that we also have to recognize is with hyperspectral data, we're getting it's that's showing up in the characteristics are non-linearities. So a lot of the methodologies, for dimensionality reduction, linear techniques like principal components are not going to give you as effective an output as some other potential nonlinear approaches. And these come from a number of sources. One is multipath reflections from all this terrain and canopies. If you have water, then you have attenuation in the water. Multiple scattering because you not only, it's not all clear water, in fact very little of it is, etc. So this shows up in the data. How can you address it? So the two things I'm going to just in this example talk about are projecting the data. So you see here 3 bands of this particular example plotted down here, and you see the manifold of this 3 bands. And so if you were to use traditional distances between the pixels in spectral space, say Euclidean, they're not going to be meaningful at all because 2 things are going to seem to be far away or close that may not actually be that. And so some of the techniques and all of the feature extraction techniques that I've ever dealt with are projections or data-driven projections onto a lower space using some criterion. And some of the new ones are going to, they're not so new in the statistical sense, but in this domain they are. So let's just look, if we're going to try to classify data, and we have these particular examples. So we have band 1, 2, and 3, 4, and 5, 6, and 7, 8. So they're representing the principal components. So you see that after about the first, actually 2 bands, you don't get much information. So you are not going to be able to separate the classes necessarily effectively. So here's another approach, a global approach that is used for projecting the data onto in a nonlinear kind of way. And you see that you have more information in terms of additional bands, but with this global approach, you're not picking up those spectrally local features that would appear in a graph embedding. And when you move to a local approach, you see that you're doing even better. So this is just to give you an idea of some directions that might be of interest. Another thing that we have found in our work, we want to do multi-temporal data analysis, and if we have hyperspectral data and we've got to project it onto a lower dimensional space, well, we've got to, that's a challenging problem for one image, but if we're going to relate these data sets over time, we've got to have some sort of projection that's stable. And so the whole knowledge transfer idea, there's a lot of approaches in the machine learning domain that are of interest. We have been working on manifold alignment using these spaces, these nonlinear spaces that we've projected onto. And this just shows you an example where, if you look at this, and this is the projection for day 1, for date 1, and so, excuse me. If we look at it for May and we look at it for June, and if we looked at it for July, it'd be a little bit different, then what we see is there's global similarities but local differences. And so what you want to do is combine in your graph embedding some kind of approach that's going to align these and project them in a way that's fairly stable. And this is just an example of looking at that May and June and May and July projection, and you see that if you align them, then you will, this is your alignment that you would get, then you could probably bootstrap yourself through the classification. Case study 2 is one that's another approach that I think is fruitful. So if you're doing mapping and you have some sort of traditional supervised classifier, you have labeled data, okay, you go through the classifier and you have output. So active learning says, I got a lot of unlabeled data out there. What can I do with it? So I'm going to have a query criterion, and I'm going to try to find the data, not that I can classify the best, but the data that I have the most difficulty classifying. It's important data to me. Now, one assumption is I have a good relationship with God, and so I'm able, from my tutor, to get some labels somehow. And so you can decide which data might be fruitful. You will take those candidates, label them, and then you will actually incorporate them in the label set. This allows you to start with a very small amount of labeled data potentially and improve your learning in a very cost-effective way. And this is just a framework for potentially doing that happens to use multi-kernel learning. It can incorporate all kinds of things in terms of ensemble classifiers, etc. Another thing is, don't be afraid to put multiple things together. We have developed lots of tools over the years. Spatial information in agriculture is very important. You have a lot of fields that are contiguous, and so everything in that field is a given crop, even though there might be a lot of variability. So you can use segmentation techniques up front, and this is just a framework in which you might incorporate segmentation and active learning, and even semi-supervised classification that would include pseudo-labeled samples. So just an extension of that framework. And this is the same thing, which just shows that there's two things that actually you can think about doing is adaptively update your features and as well as add samples both for the semi-supervised learning and for active learning. This is the most famous data set in I think it's not in the UC Irvine repository, but if you do any work in hyperspectral data, it's the one. And it's about 20 years old, and it's from 3 kilometers west of Purdue. And it's a funny story because the data were collected for something that had nothing to do with classification, and actually people have spent a lot of time trying to reproduce this output map when there's actually errors in the output, but you can guess that they're able to do it. So this is just from that case study, an example of where the first approach that I showed you is applied but does not include spatial information. And what you see in the lower right-hand corner is an output map where we have actually incorporated that last frame. We've utilized that last framework. And I'd like to point out how similar some of these classes are. So that's an illustration of why you need to incorporate spatial information as well as spectral information. I'd also like to point out Ms. Zhou Zhang, who's sitting here in the third row, who's the author of that algorithm. So the challenge. Okay, so we got lots of advances in Centrocraft, the platform technologies, and hopefully they'll be reducing mission cost in space and giving us better spatial temporal coverage from, and I'm speaking missions in the context of space, but of course UAS and constellations of small sats will contribute as well. Advances in sensor technology across the electromagnetic spectrum, and I just mentioned a few. Advances in processing algorithms. So here we are marching along. However, the incorporation of all of this advanced capability by the science and ag research and applications community is very limited. How many models incorporate much more than NDVI? And we all know that NDVI is not a calibrated measurement by and large. It could be from hyperspectral data because it's going to be over the same narrow wavelengths, but not in general. Well, there are problems, but there are also challenges and opportunities. So these are some of the things. Big data science problems are mostly multidisciplinary and interdisciplinary. Our reward structure in academia is not such that we can spend a lot of time engaging in multidisciplinary learning where we've just graduated and done a postdoc and we know a lot about a little, and we need to publish on that. But this is where the long-term research needs to go. Another thing is real problems are much more difficult than testbed problems that we use particularly in our algorithm development community. The algorithms are important, but we cannot by and large just put them on top of given data. Extensions are important, you have to understand the data, and the methodology often has to be adapted and extended. The data are important, but the understanding of this broad-based community is crucial, and you have to put your pride away because you go into these groups and there are things that you know nothing about, and you'd have to be aware and willing to be a little foolish. And finally, this was mentioned in the first plenary. Our current education structures are really not adequate for addressing the problem of developing and training our researchers of the future. And so we need to really work together on new models that will train the students and train the current researchers and work together and train us as well as faculty. So in closing, I'd like to go back to my original graphic, which says, it's an integrated system comprised of many components, but it's a challenge and a great opportunity. Thank you very much.
Thank you very much for a great talk. You probably already answered half of the questions that are coming up in the panel. But anyway, are there questions from the audience? I'd like to start with one. So you have presented your talk specifically in the context of agriculture, but most of the agenda that you presented seemed to be general enough that would be applicable to, energy and water as well. What's your perspective on how what you talked about would apply to these two other areas, or are they different?
Well, specifically, so you think about energy. Let me go to water. So I intentionally talked about water because that was the second topic of this this workshop. And so I think, the areas in which we need to transfer our thinking is rather than growing plants, although water is very important for plants. And we were talking about this over the lunch hour, so if you start with hydrology, and then we also have models for the plants, we need to incorporate them. But the water piece that's in that context very important is the water down to the root zone for plants. Now, for hydrology, then you not only have surface water runoff, but you have, in our case in the Midwest, we have tile drainage, for example. So you have to worry about water quality. So the sensing piece is going to be common to both of those, okay? But the modeling piece is different. And so, there's a need to be integrated. Now, when you talk about energy, certainly there's the bioenergy, the plants that we're developing for bioenergy. But beyond that, there's, remote sensing. That's by and large kind of a whole different field because you're going to be talking about solar, you're going to be talking about wind, you're going to be talking about, but certainly there are technologies that, are going to be addressing some of those areas.
Okay, thank you. Other questions?
Your thoughts on point measurements in the field. Obviously, we could acquire a tremendous amount of remote sense information, but a lot of it has to be validated with grounded information. And within the topic of this workshop, some of the bottlenecks, those are bottlenecks.
It is.
And there's so many avenues to try to link those two things. What's your perspective on where we should be going there with that, emphasis-wise, paralleling these kinds of platform data sets?
Okay, so the example I'd like to use is associated with, again, maybe hydrology and water quality, because the sensors are either, in those cases, dense over a small area, or more likely, they're sparse over a large area. They're watershed level. Whether you're talking about the Illinois or you're talking about a smaller river, then, you were lucky. And it has to be, an intentional investment that somebody made. We have a watershed in Northeast Indiana that is fairly well instrumented, so to speak. And it was motivated by a water quality problem downriver. So they spent years and lots of money getting them up and calibrated, and now we have these missions. You may have, one sensor, a located 1-point measurement that is going to be at depth, multiple depths, that you're going to be trying to use for something that maybe the sensor isn't even located anywhere near the center, and of course, depending on the topography, maybe that's not even meaningful. So it's really, really challenging. So the in situ sensing has to become cheaper, and it has to be much more easily deployable. And it's not going to happen today or tomorrow, but people are working on sensors that are biodegradable, that you put out there, okay, let them operate and biodegrade so you don't have these batteries contaminating the environment, etc. But I think that to actually, at this stage, then what we have to do in the meantime is we have to work on downscaling algorithms. The ones we have are not adequate. So if we take it from our, let's say we develop a multi-scale model at different resolutions, and we do some kind of modeling between the resolutions. You can do a spatial kind of a version of a hierarchical Kalman filter, for example, up and down the pyramid. But that ignores real features. It ignores objects. There's lots of challenges, but lots of opportunities. One of the downscaling algorithms uses MODIS for soil moisture right now. And my European friends say, it works great. Let me show you. And I'm looking at it, and they use NDVI from MODIS. I said, well, that's terrific. But it turns out it's all over grasslands. So as soon as it rains, whoop, up it comes. But if you have the Midwest, then you don't have that kind of immediate response, or any place you've got deep roots. So, we go with the first cut, our first naive approach, and we have to just keep working at it. But I think that in the meantime, that whole intelligent downscaling for those kind of problems where you've got point sensors and you've got coarse spatial resolution sensors, it's got to get a lot of work to get any kind of effective results.
Okay, any more questions? If not, let's thank the speaker again.
Thank you.